It is time to build a neural network to make predictions on handwritten digits of the MNIST classifier. Very exciting. To do this, we're going to need one hot encoding. By one hot encoding, I mean the following. We want to represent the number 2 as such. Okay, 0, 0, that's 0 and 1, 2, excuse me, 2, 3, 4, 5, 6, 7, 8, 9. What am I doing here? So the representation of number 2 should be the 0 for 0, 0 for 1, 1 for 2, 0 for 3. These represent the digits 4, 5, 6, 7, 8, 9. So each prediction has a 1 when it is representative of that digit. For instance, the number 8 would have all zeros except for a 1 in the 8th place. Okay, that's called one hot encoding, and we need that for keras here. Okay, so how do we in fact do that? Well, we're going to convert y to one hot encoding, and we use a keras tool called toCategorical. So from keras.utils, we're going to import toCategorical, and then we are going to use this for y. Okay, so for the y training data, for instance, we're going to use toCategorical, and we're going to put our y in there, and we do need to specify the number of classes, which of course is 10 for the digits 0 through 9. And what that will do is exactly what I've just showed you above. It's going to convert the output into the one hot encoded vector representation. Let's do the same thing for y test. We'll go with toCategorical, and this is our y test data, and of course we want the same number of classes, which will be 10. Now, we can also try to scale down the data if we want. So x is between 0 and 255, 256 pixel representations. So we could make it all between 0 and 1. This, depending on your model type, often does not make too much of a difference. I think if anything, it should only help here. It can prevent, runaway kind of values with larger numbers. Keep in mind that neural nets do find weights, which are multipliers for each of the values. Okay, so this helps to limit those weights and keep them closer to 0 and 1. Okay, so let's go ahead and run that preliminary code. And now to start our neural network, let's go ahead with our traditional keras import. So we're going to go from keras.models, import sequential. That's our left to right standard neural network sequence. And then we want from keras.layers. We will import dense, which means that everything will be densely connected. Although with dropout, we can actually limit that. And then finally, we're going to use the from keras.callbacks. We'll set up the early stopping monitor. That's called just early stopping. Okay, let's go ahead and run that code. Make sure that we have things labeled correctly. It works. So I do want to show you a visual of dropout from the original paper. And so this is kind of nice. You have sort of these two hidden layers, and you have this prediction at the end. And what you're seeing here, that some of these nodes actually drop out. And so this looks like it's perhaps a 50% dropout. And what that means is there's a 50% chance that a given node will not be included in a single iteration. And the reason why this can help with dropout is because if it finds, oh yeah, like this node is doing all the work, and then, well, it can't because it's going to be dropped out, say 50% of the time. And so it's forced to find more general pathways to the predictions. Okay, let us go ahead now and build a network. So model, we're going to initialize it as sequential. And now we're going to add a hidden layer. So add dense. And, there's no right or wrong. You just got to pick something. We've got 74 columns, I believe. Is that right? Or do we have more, right? Like, we definitely have more. And if you ever want to know, you can just gather it. Okay. You can put in here a little code, right? So what is our x train dot shape? Okay. And so it is 784 columns. Okay. 784, right? That's a lot. Okay, and so how many nodes do we want to bring those to? Well, maybe we cut it down by something like a factor of 10 and go to 78. All right, so we need to specify that input shape here, and we can do that. It's right there, it's the 784, but we can say xtrain.shape, and it's going to be the column value, and then we'll give a comma to specify the rows. And this shape needs to go in its own parentheses, okay? And after that parentheses, you can add another comma and give your activation function. We'll call this ReLU, which sends the zeros to, all the negatives, I should say, to 0, and the positives to their positive value, which is kind of nice because there are a lot of zeros in an image, that's only being filled out in the middle parts. Okay, so there's our first hidden layer. Let's do a dropout now. And so to keep it general, I'm going to drop out, again, not a right or wrong. Let's say 40%. Okay, and you do that from 0.4. Cool, and then we move on, model.add. Let's do another dense layer. And for this one, I don't know, we could go down by, let's go to maybe like half it or something, 36-ish. Be like 32. And then we don't need to specify the input shape on this one. We just need our activation function. Okay, so activation equals ReLU. And we can drop out some of these layers as well. So model.add dropout. And then I'll go with the smaller value slightly, say 0.3. So we'll keep more of those. And finally, let's just go ahead and add in the final output layer, which is going to be another dense one. It's got to have 10 because it's got to have the digits. It needs a softmax activation. Okay. And then finally, recall that the final activation is necessary for what you're trying to predict. Okay. And so, like if it was just a single value, you don't need it, but softmax is required because of this form. Okay. It's going to give like the probability that it's in, like if it thinks the greatest probability is that it's this one, it'll report back that it's this vector. Okay, so let's print out the model summary and see what we end up with. Okay, so we got 64,000 parameters to train. Okay, that's a lot. All right. So let's go ahead now and, in fact, build it and compile it. We sort of built it, but now we got to put it with the data. So model.compile. I'm going to set the optimizer to atom. The loss is going to be, it needs to be here categorical cross entropy. Okay, for that one hot encoding. That's a probability form. And for the metrics, we can go ahead and use accuracy. Okay, accuracy is just, is it right or isn't it? Great. We set equal to denote the underline. Thank you, Colab. Helps to spot the errors. And it should be metrics, plural, I believe. Okay. Next, we have the early stopping monitor. And for this, we just put in the early stopping, and we'll give it a patience. We'll give it about 10, so if it doesn't improve after 10 rounds, we're done. I would make that a little higher, but for videos, we don't want it to go on too long. Now we go ahead and fit it, so model.fit, fit it on the training data. Now recall we want a high number of epochs because the early stopping monitor is not going to let it go this long. So just a bunch of zeros. The validation split is what is, how much of that training data do we want to validate on? That's, that's what is going to verify if it's improving or not. Let's go something like 0.15. And we need to put our callbacks in here. And for now, we just have the early stopping monitor. Okay, and then finally, we are going to evaluate it on the test data. Okay, let's give it a whirl. See how we do. Okay, you can see the model is in fact building. It's showing the accuracy here on the training data. How many of the digits is it correctly predicting? And what's nice, you can also see it is in fact learning because it was going up. It stopped in the middle of building. I'm not sure why, to look into this, but if we look at the validation loss, probably it has something to do with the test set. The validation set ceased to, I think, improve, and that's why it actually stopped. Okay, so it didn't give us the value on the test set. So when you have note that the accuracy, I'm sorry, I should looking at the validation accuracy. When the accuracy is better than the validation accuracy, what that would indicate is that there's still overfitting happening. So let's take a look at this and see how we can fix it and improve it.